This is the lectures on the last sections of chapter 2 is about measures of precisions. So the first measure of precisions that we're going to learn in this course is quartiles. So by the definitions, there are 3 quartiles, Q1, Q2, Q3, and these 3 quartiles divide an order data set into 4 equal parts. Okay, about one quarter of the data fall on or below the first quartile. About 1/2 of the data fall on or below the second quartile. And the second quartile is also the median of the data set. And the third quartiles, about 3/4 of the data fall on or below the third quartile, Q3. So again, you order the data set from in a ascending order, from smallest number to the largest number, from the minimum value to the maximum value. And you divide your data into 4 equal parts. And each of the equal parts represents the positions of each of the equal parts represents each of the quartile. For an example, if you look at this is the tuition cost for 25 liberal arts colleges here, and then you are asked to find the first, the second, and the third quartiles. So the first thing we want to do is we want to put this data here into an order, right? Into an order data. And then first we're going to divide the data by 1/2 to find the median. And then on the first half, we divide it by 2 to find the first quartile. And on the second half, you divide it by 2 to find the third quartile. So first I have the data set. I put the data set in ascending order, right? So this is the minimum values, and this is the maximum value. And since I have 25 data entries, in order to find the second quartile, I can just find the median of this data. So the median would be the values on the 13th number. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3. So the median should be 32. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3. So it's the second 32. So this is the median. And then, which is Q2, right? And then Q1 will be the median of the mean to these values right here. And now on the left side, you have how many? You have 12 data points. So you have 12 data points, so that means the median should be the average of the 2 middle data. So the average of the 2 middle data should be the one on the 6 and 7. 1, 2, 3, 4, 5, 6, 7. So it should be the average of these two. 1, 2, 3, 4, 5. Okay. So this is Q2. So 26.5 should be Q1. So Q1 equals 26.5. All right. Again, in Q3, we just want to find the median of the data set on the second half. And then it's going to be the 5th and the 6th and the 7th data entry on the second half. So just count from here. 1, 2, 3, 4, 5, 6, 7. So the Q3 should be 40.5. All right. So we just found the 5 number summary for this data set. So the minimum entry is 19. I'll pick another color. Q1 is 26.5. Q2 is 32. 3 is 40.5, and the maximum entries is 46 for this data set. All right, we just found the 5 number summaries of this data set. All right, the next thing we're going to do is we can identify outliers of the data set, if there's any. So by the definition, the outliers are the values or the data entries that are far away from the majority of the data set. And in order to find outliers or identify outliers, we're going to use the interquartile range, which is just the difference between Q3 and Q1. And then the formula that helps us find the outliers is any values, right? Any values that are either greater than Q3 plus 1.5 times IQR, or less than Q1 minus 1.5 times QR. So you find IQR and you take 1.5 times IQR and you add to Q3, you get an upper bound. And then any values that is greater than this number will be outlier, or any value smaller than this number will be too far away from the left, will be outliers. So let's use the data in example number 13 to see if there's any outliers in this data set here. Okay, so again, we want to find the IQR, which is just Q3 minus Q1, and which is 40.5 minus 26.5, which will give you 14. And then, so we want to find the upper bound, which is Q3 plus 1.5 times IQR, right? Which is Q3 is 40.5 plus 1.5 times 14, which equals to 61.5. And then the lower bound can be calculated using Q1 minus 1.5 IQR, and it's going to be equals to 26.5 minus 1.5 times 14, which is 5.5. So as you know that any values, right, in the data set that is less than 5.5 is considered outlier, and any values that is greater than 61.5 consider outliers. In this data set, the minimum value is 19, the maximum is 46. These two numbers here fall within this range. So we can conclude that there's no outliers that are detected. Okay, so now we have the 5 number summary and we know how to identify outliers. We can create box plots, a box plot for a data set. There's 2 different box plots. One is just a box and whisker plot, and usually they call it box plot. This is an exploratory data analysis tool, right? An EDA tool that highlights the important features of the data set, which are the 5 number summary. And look at this box plot, you will know what is the minimum value, maximum Q1, Q2, and Q3, and so on and so forth. And then if you want to highlight outliers of the data set, you can use the modified box plot. And the modified box plot is very similar to the regular box plot. But the whiskers in the box plots, in the modified box plots, only extend to the maximum and the minimum data entries that are not outliers. So if you have outliers, you're gonna separate the outliers, and the whisker of the then the whiskers in your modified box plot will only extend to the maximum entry and the minimum entry that are not outliers. Okay, so that's the definitions of just regular box plot and modified box plot. How about if we look at this example here and we can try to create the two different box plots here. So this example represents the number of nuclear power plants on the top 15 nuclear power producing countries around the world. And first, in order to create box plot or modify box plot, you need to have the 5 number summary. So first I order the data using ascending order, right? And then using this order data, I know that this is my minimum values and this is my maximum value. So mean is 6, max is 104. Now there's only 15, there's 15 data points. So that means Q2 will be the median and Q2 will be the data point, the 8th data point, right? Because it's 15. So 1, 2, 3, 4, 5, 6, 7, 8. So Q2 will be 16. And then Q1 will be the median of this data set on the left side, the data set on the left side of the median. So we have 1, 2, 3, 4, 5, 6, 7 data. So the 4th will be 9 here will be Q1. And we have 1, 2, 3, 4, 5, 6, 7. So again, 1, 2, 3, 4. So 33 will be Q3. All right. So for the box plot, you have, you want to identify the mean values, which is 6, right? And the maximum value, which is 104. And between this mean values and maximum value, you want to identify Q1, Q2, and Q3 proportionately. So let's say Q from 100, like the difference between these two here is about 98. You divide it by 3, so then you have 33 over here. So I have Q3 here, which is 33. And then I have 9, which is very close to here, right? And 16 should be, so the difference between these two is 27, 16. So 16 should be around here. Okay. It's Q2, right? And then Q1 is here, which is 9. All right. So I'm gonna make a whisker here that go through all of this point. Again, you wanna draw it proportionately, so then you can see the patterns of the data clearly. And then you have a box around Q1 and Q3. And then you have a vertical bar that goes through Q2. So this is the regular box plot. And you say that this is the minimum mean. Is it different colors? Okay, so this is Q1, Q2, Q3, and this is the maximum value. All right, so this is the regular box plot, right? Now, how can we make the modified box plot? Again, modified box plots highlight the outliers. That means we need to find outliers. Is there any outliers here? We can try, so we can try FIIQR, which is equals to 33 minus 9 is 24, right? And upper bound is which is 33 plus 1.5 times 24 is 69. And lower bound which is 9 minus 1.5 times 24, which is negative 27. So any values that are greater than 69 or less than negative 27 are outliers. So we know that the mean is a positive number, so we don't have any values on the left, but we might have some outliers on the right. So what are those numbers that is greater than 69? We have only one, which is 1.4, 104, which is the maximum value. So outliers okay. So I want to make the modified box plot here, and I want to start at the same minimum values, and also I want to end at the same maximum value. But as you can see that because we're using modified box plot, the whisker will not extend to the maximum or this outlier. So 104 here is actually an outlier. And we still have, and then the maximum values in the data set, that is not the outlier, is 58. So I only extend my whisker up to 58. Let's see, it's 58 right here. And I make a box out of Q1, Q3, and a vertical line through Q2, just the same as how I make the box plot up here. So this is the modified box plot for this data set. And if you look at the modified box plot, you know right away that I have an outlier. And the distributions of you can see you have a better understanding of the distribution of the data set if you when you exclude all the outliers compared to using the box plot when you include all the values in the box plot. All right, the next section is about percentiles and other fractiles that you can use as a measures of positions. So we will discuss about quartiles when you divide the whole data set into 4 equal parts. If you use these styles, that means you divide the data set into 10 equal parts, right? And you have D1, D2, D3, D9. And if you use percentiles, then you divide the data set into 100 equal parts, percentage, P1 to P99. So the definitions of percentiles and how to find the percentiles of any data entries in a data set is you can find the percentile of X equals to the number of data entries less than X divided by the total number of data entries, and you multiply to 100 to get the percentage. Okay. Again, number of data entries less than X divided by the total number of data entries. So look at the example number 16. If the student's test grade of 75 represents the 65 percentiles of the grade, what percent of the students score higher than 75? Okay. So again, the percentiles represent the number of data entries over the total number of data entries. So if 75 represents 65 percentile of the grade, then 35%, right, of students score higher than 75. Because 60% of the students score lower than 75. That means 35% of students would score higher than 75. The next example is March of 2013. There were 665 oldies radio stations in the United States. One station finds that 106 stations have a larger audience than it has. So what is the percentile does this station come closest to the daily audience rankings? What is the rank of these stations when there's 106 stations have a larger audience than it has? So another way to answer this question is find the percentile, right, of these stations. It should be equal to the number of data entries less than these stations, less than the number of data entries that has a smaller audience than these stations. And it has 106 stations that have a larger audience. That means you have to take 665, right, minus 106 and minus 1, which is the station that we are looking at. And then you divide it by 665. Does that make sense? So you find this is the total number of stations, and this is number of stations that have larger audience, and this is the station itself. To find the number of stations that has smaller audience, and then divided by the total number of data entries or the total number of stations, and you multiply to 100. And you would get the answer for, it should be 83.9%. So it's roughly, you can round it to 84% percentile. All right. And then the last part of this sections is about standard score. Again, we're going back to the idea of how can we interpret the standard deviations. Once you find the mean and the standard deviation of data set, you can measure the position of any entry in the data set with a standard score or the z-score. Again, earlier when we talked about standard deviations, we only can measure the positions of like data entries that is 1 or 2 standard deviations away from the mean. But if you use a standard score or the z-score, you can measure the position of any of the entry using the mean standard deviations. Okay, so the standard score or the z-score again represent the number of standard deviations of a value x lies from the mean mu. Number of standard deviations. It can be a whole number, or it can be a fractions, or it can be a decimals number of the standard deviations of that values lie away from the mean. Okay, so the formula to find the z-score is you take the values that you're looking at, x, you subtract the mean, and you divide it by the standard deviations. Again, you take the values, subtract the mean. This is the value that we're looking at, right? You want to see how many standard deviations away from the mean this value is. Then you take x minus mu and divide it by sigma. So let's look at the normal distributions again, the bell curve distributions that we talked earlier, right? And then you always have the mean here. And then you would have, let's say I have an x values right on the mean plus 1 standard deviations. Let's say x1. This is the values of x1. And I have, this is the values of x2. And this is mu plus 2 standard deviations. Okay. So in order to find the z-score for x1, let's say z-scores for x1, I take x1 minus the mean divided by standard deviations, right? And I know that x1 equals to mu plus sigma. I replace mu plus sigma and then divided by sigma. And what I get from this is going to be 1. So let's say if x1 equals to mu plus sigma, then my z standard deviation, the z-score is 1. And you know right away that this x1 here is 1 standard deviations away from the mean. Now go to z of x2. Z of x2 is values in between these two, right? Mu plus sigma and mu plus 2 sigma. And I don't have any special information about x2, but then I can still find the z-score for x2 minus mu divided by standard deviations. And you know that z of x2 here should be greater than 1. And it should be less than 2 because it's not 2 standard deviation away from the mean just yet. And you can use the same formula to find the number of standard deviation away from the mean for values that are on the left of mean. So this is like the middle of the data set. Okay. All right, so this is how you find the standard deviations, find the standard score or the z-score of any of the value in the data set using the mean and the standard deviations. Now let's look at an example here, example number 18. A university admissions office needs to compare the math scores of 2 applicants who took different standardized tests during the senior year of high school. The first student took the SAT test for which the average math score was 500 and the standard deviations of 100. Okay, and then the second student took the ACT test, a common alternative test to SAT, which has an average score of 22 and a standard deviation of 5. So the first student had an SAT math score of 640, and the second student had an ACT math score of 28. Use a calculator to determine which of the two had a better score. Give an interpretations of your calculations. All right, so again, there's 2 different tests that have 2 different distributions. One has a higher mean and higher standard deviations. One has a lower mean and the lower standard deviations. Okay. Then I can come up with the 2 distribution for the SAT and ACT test. Let's see, I have it here. So for SAT, the mean is 500 and the standard deviations is 100. For ACT, I have the mean is 22 and the standard deviations is 5. Okay. Now the first students took SAT, so I see x1 is 640 and x2 should be 28. We want to compare between the student who did better on get a better score relatively to the same math test. That means you want to find how far away each of this test score, how far away each of this test score from the mean. The further is away from the mean, the better the score is, right? And how can we determine the positions of each of these values in this data set? That is when we're going to use the standard score, the z-score. the z-score here to tell you how many standard deviations away from the mean that this value is. Okay, so in order to find the standard score, the z-score for x1, I take the values x1 minus mean, which is 500, divided by the standard deviations. Similarly, I'm going to take find the z-score of x2 within this distributions, because so between SAT and ACT you have two distributions. In order to find the z-score, you have to use the mean and the standard deviations in the same distributions. So it should be 28 minus 22 and divided by 5. Let's see, 28 minus 22 divided by 5 is 1.2. Okay, so 640 minus 500 divided by 100 is 1.4. Since z of x1 is greater than z of x2, then the student 1 did better than the student 2. Right. If you compare their scores within the same distribution, within the same populations. Okay. So again, if you have two different scores, two different values from two different populations, and you can compare the two score together if you convert the two score into its standard score or its z-score. So you have to convert it to the same measurement, to the same metric, which is the standard score, the z-score, before you can compare the two values together if they are from a different population and different distributions. So this problems here ends the 5th sections of chapter 2. And again, chapter 2 is about descriptive statistics. You learn techniques and methods on how to organize, display your data, and learn, explore your data in terms of the mean, the central tendency, in terms of the variations, and in terms of the positions of your data in the data set.